So let's do our first example. It's going to be an algorithm very similar to linear search. Now, for those that are familiar with this problem, you know that linear search can be used to solve this problem. That's simply where we sequentially go through each one of the elements in the array, and we just examine each one. If one of them is X, then we're done, right? We found the position where it is, so then we can just return that value. But if you have to examine all of them, it may be the case that that happens. That's when you know, hey, look, X isn't here. The key isn't here. So I'm going to consider a variant of linear search. I'm going to call it kind of linear search. We're going to call it kind of linear search. It's going to have, I'll call it the array A. Doesn't make much of a difference as long as we're consistent about it. We have our array A, it's of length n, and it has X. It's the desired key. So usually it's a good idea to say what the input and output are, but I don't want to make any claims about if it's correct or incorrect. So I'm just going to omit the output part, but if you wanted to put something there, you could just say returns an integer, because we don't know if it exactly solves the problem yet. Because remember, the solution is going to take the form of an integer that represents the position in the array. So I call it kind of linear search. You're going to see why. This is why I call this a pretty easy example. So watch this. So we're going to have a for loop. We're going to start it at position 0, and it's going to sweep from left to right up to position n-2. Now let's hold off for now. Let's make sure we understand what the algorithm is. So we check if a sub I, I'm going to check the value at position I in A. I'm going to see if it's equal to X. If that's the case, then I'm just going to return that position because I got a match. However, if I am able to go through all these positions, I'm going to return -1. So a question for you. Can you show that this algorithm's incorrect? So how many of you think that this is actually a correct algorithm, though? There's a reason why I call it kind of linear search. It's not quite linear search. Let's go through an example just to get a flavor for how this works. So let's do an example. Let's use an array of length 6. It's going to have 6 elements in it. Let's go 6, 5, 1, 2, 4, 20. So that's why the 20 is in the last position, but let's try it when x is equal to 2. So the key is 2. So what this says is that we're going to start I at 0. And what it does is that starting at 0, it checks if a sub 0, which is here. It tells me, so I go to position 0, I check a sub 0, that's 6. That's not equal to x, which is 2. So I don't return I here. Instead, I proceed to the next iteration of loop. Now I is incremented by 1. Now I is 1. So I is 1. I check a sub 1, that's 5. 5 is not 2, right? So we're going to proceed to the next one. Let's go to the next iteration. We check 1. So I, right now, after that iteration from I is 2, it's now going to go I is 3. So now I check a sub 3 is equal to 2, but that actually equals x, right? So in this case, it returns I, which is going to be equal. So you know the solution in this case, by the way, was position 3, right? And in this case, the algorithm does return 3. It ceases to continue computing this algorithm, right? So it returns 3, and it does not proceed with any more computations here, okay? So that seems pretty nice, right? So I've alluded to you that this algorithm is actually incorrect. What's wrong with it? So the hint's in the name of the algorithm. So remember, the burden for us is to present a counterexample. Now, first, I'm pretty sure everybody understands this guy, right? It's just simply go through each one of these, sweep from left to right. However, we stop at index n-2. I want you to take notice of that. That's a very important detail here. So first, understand what the algorithm is. Now what I would like to do is try to outsmart the algorithm. So this is a very common way of kind of getting yourself into the mindset for doing this, is think about trying to outsmart this thing. Remember, there's no intelligence or anything here, right? Even then, it's just an algorithm, right? Algorithms aren't like, there's no intelligence here. There's no agency. But notice here that suppose I look at that. It seems like it's not really going to the last position. Do you see that? It goes, so it would go, when I is equal to n-2, it goes through here. If it fails to find a match, it will increment it by 1 to n-1. It'll cease this for loop. And it'll just proceed to the return statement. So let's take advantage of that fact. So let's change up this instance a little bit. So we know that this algorithm isn't actually checking the last position. So let's change it to 20. And we know the solution in this case should be 5. It should return the last position. However, what's the algorithm do? As I just explained, it's going to return -1. -1 does not equal 5. That means it's not producing the correct output. Hence, this algorithm is incorrect. To do this, I established that by using a counterexample. Now you might say, Dan, that's just one example. Is there a way I can better describe what's actually happening so it can better inform me how I can fix the algorithm? And this is the big tip I really want to give you, is that just getting an incorrect result isn't the end of the story oftentimes. Sometimes it's just the start. So, for example here, notice that I don't examine the last position. I can characterize this counterexample actually as a whole set of instances that all have this property. So notice that any one counterexample looks like this. There is a set of instances that look like this. Now remember, I've just presumed that everything we're working with is an integer. So imagine I give you an array A, an arbitrary one of length n, where you imagine you give me the key x, right? I make all of the entries in the array except for the very last position. All these are not going to be x, right? Except for the last position. Do you see how this defines, in fact, if I really want to go really just all into this, I could define an infinite set of instances akin to this by just simply making it so that x is equal to, let's say, make it 2. Then what happens is this would be a 2, that's 1, 1, 1. These are all 1s, and then there's a 2. But notice that there's an infinite number of them because I've given you a way of characterizing this for an arbitrarily length array, right? So this gives you everything you need to know about what's wrong with our algorithm. Do you see that? So this is actually telling you that the last position isn't getting examined. So I'm not going to prove this here for you, but this would be an example of a set of counterexamples. Each one is an array of length n where all of the positions except for the last one have 1 in them, and the last position has 2 in it when the key is 2. I'm not going to prove this here for you, but if you just switch this to n-1, this will work correctly. Do you see how now I'm actually accounting for that last position? Because the correctness of such an algorithm is based on needing to examine every one of the spots, right? Seems kind of straightforward. At least I think it is. I don't like to say that, but I hope that you see or appreciate that fact. And in fact, what I wrote here is linear search. So it's not just kind of linear search. This is linear search now. And you can clearly say that, yeah, look, it's going to return the position where a sub I is equal to x.